All right, here's an f of x, and we want increase intervals, we want decrease intervals, and we want local extrema. So all those things come from the derivative. We better get one. df dx. Now, you may remember that the derivative of sine is cosine. We need that here, of course. So the derivative of 3 sine x is 3 cosine x. The derivative of 2 is 0, so that part's gone. And we're interested in the places where this derivative is either 0 or undefined. Those are what we call the critical values, or the critical numbers. Cosine is defined everywhere on XER, so there's no undefined places. But there are certainly places where it equals 0. In fact, there's an infinite number of them. Cosine is 0 at where? Places where the x-coordinate on the unit circle is 0. That would be 90 degrees, or pi by 2, and 270 degrees, which is 3 pi by 2. And I could go on for all eternity, but we really only need these because they've asked over the domain 0 to 2 pi. These are the only places on 0 to 2 pi where cosine hits 0. So let's conjure up a number line here. Here's pi by 2. Here's 3 pi by 2. We're going to look exactly on those points, and we're going to get 0, but in general you want to check on those points and you want to check around those points, and we want to see the behavior of 3 cosine x. So if x is lower than pi by 2, let's say it's 45 degrees or something like that, cosine x comes out positive. At pi by 2, which is 90 degrees, cosine is 0. Between 90 and 270, we're over in quadrants 2 or 3, cosine is negative there. At 270, cosine is 0. And as we go past 270 into quadrant 4, cosine goes positive. So that tells us that the 3 sine x plus 2 is increasing, flat, decreasing, flat, and increasing, which does indeed look like how a sinusoid behaves. So we can say that our intervals of increase, let's see, we increase from 0 up to pi by 2. And we also increase from 3 pi by 2 up to, but not including, 2 pi. I know the interval up here includes 0 and 2 pi, but technically, this is a really hair-splitting point, but you can't say the function is increasing at 0 because the function is not differentiable at 0 because that's where the domain ends. That's barely even worth remembering, but if you have endpoints, you can't say that you're increasing right at the endpoints. It's the same argument for saying that you can't have a local maximum or minimum right on an endpoint. It's because the derivative has to exist, and the derivative is a two-sided limit, so it can't exist right at the edge of your domain because you don't have two sides there. You'll probably never need to think about it again, but I thought I'd put that out there in case you were curious. So those, in my humble opinion, are the intervals of increase. We also have an interval of decrease, which is between pi by 2 and 3 pi by 2. La 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 la. Here at pi by 2, we have a local maximum. It goes increasing, flat, decreasing, so that's the top of a hill. And that local maximum would be pi by 2, comma, and how high is our function at pi by 2? Well, sine pi by 2 is 1. Triple that, you get 3. Add 2, you get 5. So that's the highest this function ever reaches. And over here we have a local minimum because the derivative goes negative, flat, positive. That's the bottom of a valley. So 3 pi by 2, comma, and what's the value there? If we're at 3 pi by 2, we're 270 degrees. The sine of that is negative 1. Triple that, you get negative 3. Add 2, you get negative 1. That is the lowest this function ever gets. So the pi by 2 one is a local max, and the 3 pi by 2 one is a local min.